solid-state chemistry of bulk mixed vanadium, antimony, molybdenum, niobium oxide catalyst for the selective oxidation of propane to acrylic acid. Combinatorial approach.
Thank you very much for having me here. For this part of the day, we're going to talk about the solid-state chemistry for bulk mixed oxides, which include vanadium, antimony, molybdenum, niobium oxides, which are proposed mainly for selective oxidation of propane to acrylic acid. And here I will, show some combinatorial approach using these kind of systems. First thing I will try to address is that when we speak about selective propane oxidation, we are talking about this kind of reaction, which is taking propane to propylene and further oxidizing it to acrolein and then getting acrylic acid. And these kind of reactions are quite attractive since we have a huge abundance of alkanes like propane. Also, by converting propane to oxygenates, as well as even for propylene, we are increasing the value for this kind of process. So converting alkanes to highly demanded olefins and oxygenates is one of the objectives of studying this reaction as well. So far, the bulk mixed oxides studied for selective propane oxidations are mainly three systems. The first system is the vanadium antimonate, and this was proposed by Bratzel in PP, and was mainly used for propane oxidation to acrylonitrile. The second system was by Mitsubishi. It's also a US patent, which is composed with a four mixed oxide system between vanadium, molybdenum, niobium, and tellurium. The one related to our system, which is one proposed by Tobagase company, it has vanadium, antimony, molybdenum, niobium species. And this was found specifically promising for the selective oxidation of propane to acrylic acid. As you can see here, as you add more metals, you increase the complexity of the system. And those represented the mixed oxide, it has multi-phases, like the vanadium antimonate, some defect phase, quote-unquote, of vanadium, molybdenum, niobium phase, some molybdenum vanadate phase, the famous vanadium pentoxide phase, molybdenum oxide, the alpha antimony oxide, and tellurium oxide. So you can see actually by having this system, the complexity of phases increases. What would combinatorial tools give us here? Since we lack the fundamental studies of the structural activity for those systems, and since we are dealing with multi-system, combinatorial tools can give us greater performance to investigate this complex parameter space and give us a great deal of information about propane oxidation toward acrylic acid. So the objective of my talk is to provide fundamental structural activity relationships for propane oxidation over this mixed oxide, which include vanadium, antimony, molybdenum, niobium, as well as to give you an integrated high throughput methodology for the heterogeneous catalysis for this system. Question may arise, why combinatorial techniques? And here I'm quoting to Technology Vision 2020. I know one of yesterday talker also referred to this method, but here actually they refer to another point, which is that in quotation there is a critical need for integrated combinatorial methodology that can provide the rules for molecular design of heterogeneous catalysis for gas-phase reaction. And especially with this system, which has a complex parameter space, there is a quite big need. And to illustrate that, in a classical approach, there are four major points in designing any catalyst. First of all, selecting the constituents or designing the catalyst itself, synthesizing, characterization, and then testing, and the cycle goes again. So if you change any parameter, you have to do the cycle all over again. In combinatorial technique, you can keep the same design environment the same synthesis environment and same characterization environment and testing environment, and keep actually changing the parameters, and this will save a lot of time and effort since we are conserving the environment for synthesis, characterization, and testing as well. One of the very recent published research by CEMEX, they managed to have actually a microreactor which have 8 by 12 array of 1 milliliter vials, and they use this system for selective catalyst oxidation for alcohols. And by this methodology, if we open this reactor, we can see this kind of vial arrangement. You can expose different compositions of your catalyst for the same environment, and this way you can detect which is the best system for your case. In terms of reactivity differences of fluoroalkane, I am speaking about ethane, propane, and butane. In a very established system like vanadium pentoxide, this chart mainly shows the relative reactivity differences of those alkanes. The one we are concerned about is propane, and you can see actually as you go higher in conversion, there is a huge decrease in selectivity towards olefins. And this shown for the different alkanes used. Going back to the bulk mix oxide used for this system, and this table summarizes whatever has been done so far for systems similar to the one we are studying. The one studied by PP at 480 degrees C, they managed to get 55% acrylonitrile at 18% conversion. Mitsubishi managed to use this catalyst at 400 degrees C to get 70% acrylonitrile at 28% conversion. For the mixed metal oxide proposed by Tuagase, and we are using in this talk, at 400 degrees C, we managed to get about 30% acrylic acid at about 31% conversion. It's like feeding propane, getting 30% conductivity to acrylic acid. So when speaking about this mixed metal oxide, there is a report that shows this is high. It has high selectivity to acrylic acid, and also it is a way to provide opportunity to test combinatorial techniques and high throughput techniques to study bulk microstructure and catalytic properties. And unfortunately, there is very little known fundamentally about this system. Actually, the patent shown by Tuagase show one face for this kind of system. High throughput experiments can include rapid reproducible synthesis, or structural characterization, or in situ characterization of active sites, kinetic testing, as well as data handling. In this part of the talk, I will really emphasize on the rapid synthesis. And speaking about synthesis for this mixed metal oxide, since we have vanadium, antimony, molybdenum, and niobium, we use these reagents. Ammonium metavanadate as a source for vanadium 5+, antimony trioxide as a vanadium for antimony 3+, ammonium heptamolybdate as a source of molybdenum 6+, as niobium oxalate as a source for niobium 5+. And there's a great deal of redox reaction goes place in aqueous solution as you mix these together. And these reactions are as follows. First of all, we have the reaction of vanadium 5+ with 3+, antimony 3+, a redox reaction that will exchange the charge of vanadium going from 5+ to 3+, and antimony going from 3+ to 5+. This is normally done at 120 degrees C overnight under reflux conditions. Another interesting reaction happened simultaneously with the first reaction, with the reaction of vanadium 5+ with vanadium 3+. As soon as we get vanadium 3+, it will react like promptly with vanadium 5+ to give vanadium 4+. Molybdenum 6 plus will react as well with vanadium 3 plus, and so these are competing reactions, even though third reaction is much more faster to give molybdenum 5 plus as well as vanadium 4 plus. The good thing about molybdenum, if we have bubbling oxygen, it is easily oxidized to molybdenum 6 plus, and it can goes back and do the third reaction as well. For the synthesis, we use the ChemSpeed ASW 2000 synthesizer, and we use this system to synthesize two compositions of a mixed vanadium, antimony, molybdenum, niobium mixed oxide. And the procedure for the synthesis is that we provide them with the water-soluble reagents for vanadium, antimony, molybdenum, niobium, which I showed a couple of slides ago, and we give them a procedure for the synthesis. So what they did under full automation, they conduct in their machine the solution redox reaction under the same environment, and they dry the catalyst also under the same environment. And then they ship our catalyst back to us from Switzerland, and then we get these, characterization and characteristic for this catalyst. And the next step for us was to test if those catalysts done automatically match the same characterization as the one which are done manually. And the first thing we done is XRD, powder diffraction. The first thing actually I will draw your attention for in this chart, before going into details, it shows quite a big deal of phases available here. And those phases are listed here. We have the molybdenum vanadate. We have a defect phase which have its kind of structure, which include molybdenum, vanadium, niobium. We have molybdenum oxide. We have vanadium oxide. We have antimony vanadate. And maybe this will show some kind of, the system we are dealing with is not of easy complexities, like quite complex. But we managed to see these phases in the XRD results. If I go back to this chart or a graph, actually, A show the manual synthesis that we done in our lab, and from B to I are the 8 syntheses done by ChemSpeed and their synthesizer. And it show a great deal of compatibility in terms of the phases, and even under a quantification of the phases, they were within 5% differences between the manual and automated synthesis. Furthermore, we done Raman spectra for both manual and automated methods, and show actually some typical pattern of that's shown in this slide. That we have a Raman shift that corresponds to this vibration, which is molybdenum, oxygen, molybdenum interaction. And we have Raman shift at around 870, 880 volt peak, which corresponds to molybdenum, oxygen, other metal, and here we are told that this should be vanadium. As well as we have a sharp peak, which corresponds to the terminal molybdenum oxygen vibration. And this actually pattern was shown in both automated and manual synthesis. This slide shows the infrared spectroscopy results by varying the composition of our mixed metal oxide. And maybe in this part show that we vary the composition of vanadium, antimony, molybdenum, niobium, and regardless of the information of different composition, we see some common features. The main feature we see actually that we have the vibration that of vanadium, oxygen, molybdenum, oxygen, and also the bridging molybdenum, oxygen, molybdenum, the bridging vanadium, oxygen, vanadium. Some interesting, vibration for the beads that correspond to vanadium and antimonate, as well as a symmetric molybdenum, oxygen, molybdenum. This, IR confirmed that we have the presence of VSPO4 by having these, broad peaks, V2O5, as well as molybdenum oxide phases. In order to assure that our results by XRD and Raman We further do some SEM, scanning electron microscopy experiments. And under 30,000 magnification, we managed to see actually there's like, these kind of morphology. And by doing EDS, we managed to get this kind of, structure, which is comprised of vanadium, antimony, molybdenum, and niobium oxide. Also, we've seen some other, morphology, which is of, much more, less organized pattern, which correspond to the vanadium antimonate. So SEM show that, there's a presence of those two phases, the antimony vanadate and molybdenum vanadate, in the system, along with molybdenum oxide. Further in electron microscopy, we did the TM, transmission electron microscopy, for those systems, along with energy-specific spectroscopy, EBS. And this baby graph shows a kind of repeated morphology we have in our system. We have this shape of crystalline structures, as well as this bulky, irregular shapes, as well as this attached, pattern. And as we do EDS, we managed to distinguish these phases. That this corresponds to molybdenum oxide, this corresponds to antimony vanadate, and these kind of, bulky-looking phases, which may show that they are not crystalline, but by doing, diffraction patterns, they are pretty crystalline material. Show, a composition of both phases, molybdenum vanadate, as well as defect phase of molybdenum vanadium niobium oxide. By going further, actually, and seeing the constituents of those phases under TM, before I go there, actually, these TM actually results, also confirm actually the Raman results we've seen earlier. Molybdenum oxide, one of the dominant phases we have there. And I showed this slide maybe a while ago, and now actually we can see a better understanding of what's going on here. This, sharp base of molybdenum oxygen and molybdenum oxygen molybdenum confirmed actually the presence of molybdenum oxide. This peak, which we are suspected that was molybdenum oxygen vanadium, now we are sure that it's molybdenum oxygen vanadium by TM results, as well as it can be this part of the defect phase. Now going back and trying to have a closer look under TM. Again, we've seen this kind of morphology which corresponds to molybdenum oxide, and by EDS we managed to distinguish the phases. That's molybdenum oxide, and there is a mixed vanadium antimonate, molybdenum vanadate phases around the molybdenum oxide, as well as in this region. By trying to magnify the region of the surface of molybdenum oxide, we managed to go to atomic level resolution and managed to see that molybdenum oxide is the main bulk phase shown here. And the interesting part here that at the surface of this molybdenum oxide, there is a mixed vanadium antimonate as well as molybdenum vanadate phase. So this phase is shown as also as a discrete bulk phase as well as a surface phase, even in molybdenum oxide. Some more images in TM that show other morphology under atomic resolution. This shows actually the defect phase of vanadium molybdenum niobium mixed oxide under 800,000 magnification. Again, the bulk show this composition. The surface show the mixed oxide of vanadium antimonate and the vanadium molybdate. Another area in our system show the mixed vanadium antimonate as well as molybdenum vanadate phase as a bulk and a surface phase under 500,000 magnification. So what did we learn from SEM-TM? We learned actually that there is the presence of active phases needed for selective oxidation of propane, which are the antimony vanadate and molybdenum vanadate. And those active phases, antimony vanadate and molybdenum vanadate, were both present as separate bulk phases by themselves, discrete phases, as well as supported on other surface of molybdenum oxide. For sure, maybe the optimum, goal for this system is to try it on propane oxidation. So what we tried recently to try this catalyst of vanadium, antimony, molybdenum, niobium mixed oxide with this kind of atomic proportions to do propane oxidation. And this catalyst, as you can see here, actually it has pretty low surface area, which is one of the bottlenecks for those systems. The feed composition we feed for the reactor comprises 4.4 volume percent of propane, 7% oxygen, and water of 2.4 volume percent, and the balance as nitrogen. We set the system from 350 degrees to 450 degrees C and under atmospheric pressure. The results show the following. Here I'm showing actually two kind of results. The one show actually in blue are the reference we've got from the patent results for selective oxidation of propane to acrylic acid, and show actually this curve which is going all the way up. That's the conversion, as in the case temperature conversion goes up, and the one having a concavity here is concave down is showing the selectivity and has a maximum selectivity at around 400 degrees C. We try to run the same composition in our reactor, and we get somehow similar trend, especially in terms of selectivity. We manage actually to get selectivity maximized at around 400 to 420 degrees C, and give at about 35% acrylic acid yield, which is pretty high for practical purposes. There's some differences in terms of the conversion. We have a much flatter conversion line along the temperature range we are dealing with than the one reported in the literature. But the only one reported in the literature is a patent, so there's not much information about what's the reasons that we are showing here. But anyway, the main outcome I want to get out from this chart that we managed to get about 35% acrylic acid yield using these kind of catalysts. So in conclusion, we managed to study high throughput experiments, and it managed to provide us rapid reproducible synthesis of mixed metal oxide, which include vanadium, antimony, molybdenum, niobium mixed oxide. This system of vanadium, antimony, molybdenum, niobium mixed oxide show great promise for oxidation taken directly to acrylic acid. Furthermore, this system comprises of many phases, and that's a little bit disagreement with whatever shown in the literature. It has those phases which are vanadium antimonate, molybdenum vanadate, a defect phase which comprises of molybdenum vanadium niobium as well as molybdenum oxide. And in terms of combinatorial techniques, I think what's need to be done next is to do rapid structural characterization for those systems, as well as in situ characterization to study the active sites in the system we are dealing with, as well as rapid kinetic screening. I would like to end by acknowledging ChemSpeed in Switzerland for their help in using their system to synthesize the mixed metal oxide we deal with, as well as Dr. Bonnet Bolchang in the Brazil Cincinnati for us using the Raman unit to present the results today. Thank you very much. I'd be glad to get your questions.
I was wondering what you learned, whether you can devise another way of making that catalyst. It looked like with your defect phases, a lot of those materials were supported, if you would, on molybdenum oxide. Could you think of starting, say, with molybdenum oxide and put down a deposit in this approximate stoichiometry that you want, and would it give you, or do you think it give you something similar or totally different material?
That's a good point. Unfortunately, those defect phase as well as the vanadium antimony phase, molybdenum as a reagent during the acid synthesis act as a promoter to get these cases. So without molybdenum oxide during synthesis, we may not get the same defect phase we are looking for. The second point is that molybdenum oxide may not be an active phase for this kind of reaction, but may act as a support for our systems. And the proposal we have in mind now, actually, that the surface layer is the major layer to do the catalysis.